Hello everyone. I think this is the fourth Ansys Fluent tutorial that we are going to do it together today. This tutorial actually considers flow within 2D axisymmetric co-rotating cavity system, or disk I would say. And let us take a look at the problem description first, and then you'll see what we can do with this simulation. So here is the problem setup. You have a disk, you have a rotating disk with two side walls on the right and left side, and then you have an outflow, and then there is an inflow of constant inlet velocity, and as you see, the whole system is rotating around this axis with the speed of 71.08 round per minute. So the dimensions are given here in this geometry. Actually, this geometry and the mesh is already created, and I have uploaded somewhere in the internet, and I'm giving you the address so that you can download it and use it step by step in this tutorial. So if I close this problem setup, problem description, so we are going actually to set up a 2D axisymmetric model with swirl using a rotational frame of reference. And then we use RNGK epsilon model, and then we calculate the solution with pressure based solver, and then at the end we show some vector plots and contours, or perhaps some XY plot of radial velocity and y plus. So if I double click on the setup, as I said, I have the mesh and the geometry already created and imported into this setup. So 2D serial, I'm not going to use this double precision, so just click OK. So the mesh is loading. So here is the geometry and the mesh. So if I go to this display, you see that I have an axis which is called axis 5, and the axis is actually located here, and then I have this pressure outlet at the top. So here is my pressure outlet, and then I have a velocity inlet, which is this one, the blue one, and then I have a wall. If I just show the wall, you can see that this wall is this wall consists of two side walls, one on the left and the other one on the right. And this is the geometry, this is the mesh that is already created and imported to the Ansys Fluent. So when it comes to the model, I have already selected the viscous option and the K epsilon 2 equation model with RNG. And I have used this differential viscosity model and swirl dominated flow options active. Actually, these two helps to get better convergence and more accurate result when the flow involves some swirling motions. And actually, I've used this enhanced wall treatment. So you know that when you use this enhanced wall treatment, the y plus should be around 1. And actually, with y plus 1, you can resolve the buffer layer and this viscous sublayer, and of course you get some more accurate results close to the wall. So that was about the viscosity model. The material, I've kept the material as air, and all default values for the air. Density and the viscosity is Ansys default values. And when it comes to the cell zoom conditions and the fluid, if I double click on that, actually I have activated the frame motion, because the whole fluid zone is rotating around the axis that is already created, and I have specified the speed of 71.8 round per minute, constant value, and I click OK. So the boundary conditions, as I said, the axis is set to axis boundary condition. Pressure outlet is set to pressure outlet with the gauge pressure of 0 Pascal. and then the velocity inlet. I have chosen the velocity specification methods like components, and I have put the axial velocity of 1.146 constant value meter per second, no radial velocity, no swirl velocity, just constant axial velocity, and I press OK. Regarding the wall, actually I've put the stationary wall, but this means that the wall is actually stationary with reference to the fluid to the boundary zones that are already rotating around the axis. So this, although this is a stationary wall, but they are actually rotating around the axis themselves. So I press this one OK as well. So regarding the solution, if I come to the methods, I have used this scheme as coupled, and the pressure spatial discretion, I have used Presto. Presto is actually suited for steep pressure gradient involved in rotating frames, so this is a good combination with the coupled pressure velocity coupling. And I have used second order upwind for turbulent kinetic energy. Everything is second order upwind here for swirl velocity and momentum as well. So when it comes to monitor, residuals, constant, the same default values for continuity, x velocity, y velocity, swirl, k and epsilon. But I have created a report file. I've actually created a report file which is the mass flow rate at the pressure outlet. So I would like to plot this mass flow rate at the pressure outlet every iterations, and so here is the mass flow rate, report type, and the surface is selected as pressure outlet. And I'm actually going to plot it every iteration. So I would just initialize the solution with the hybrid initialization, so it was quite fast, and then I would like to run the calculation for something like 600 iterations, but before that I have to say that I have used this pseudo transient simulation, because the pseudo transition enables an algorithm in the coupled pressure based solver which adds unsteady terms to solution equations, and these unsteady terms actually help the solution to improve stability and convergence. This is a good option actually, and in most of my simulation I use this pseudo transition, which enables faster, not faster, but better convergence and better stability. So when I'm coming to run calculation, since the pseudo transient is active, actually you can put the time scale factor as a default value of 1, or you can increase it so that you can have faster convergence, but the faster convergence does not really guarantee the more stable and more accurate result. So I'll just keep the time scale factor to 1 and put the number of iteration to 600 and I just press calculate. So you see this is the mass flow rate that is being plotted, and here in the window number 1 you see the residual for continuity, x, y velocity, swirl and k epsilon. So this simulation is quite fast, so I don't need to pause the simulation or pause the video recording, so we can just wait for a few seconds until the solution is converged. $400. Seems like the mass flow rate is quite converged. There is no much oscillation, but you can take a look at it later. The calculation is completed. So let's go to the post-processing. Take a look at fluxes, report fluxes, and I would like to see the mass flow rate in the pressure outlet and in the velocity inlet as well. So if you look at here, the mass flow rate in the pressure outlets and the velocity inlet, and the net difference between these two is something like 1.59 to the power to the power 10 minus 7 multiplied by 10 to the power minus 7. So you see that the net difference between the pressure outlet mass flow rate and the velocity inlet is quite very small, and this guarantees that the solution is quite converged. So if I close this one, and let's take a look at some vector plots. I have already created some vector plots, but we can do it together again here. So I would like to take a look at the velocity and the velocity magnitude, for example, with the scale of 50. Sorry guys, I have a little cold today. But then the vector options, since this has a swirl motion, I'm not interested to look at the Z component, so I just deselect the Z component and press apply. Then I put the skip to 1 and then display. So here you see the velocity vector. So if I zoom in a little bit, you see that the velocity magnitude close to the walls, side walls, and of course the axial velocity in the inlet, which is forming kind of swirl motion in the middle as well. We can also take a look at the radial velocity. Instead of velocity magnitude, you can choose this radial velocity, and you see the radial velocity is actually quite high in this region compared to the rest of the flow field. We can take a look at the contour plot of velocity as well. So here's the velocity magnitude, for example. This is already filled. So you see that the velocity magnitude toward the sidewalls at the end of the pipe or at the end of this disc is quite high, with the swirl motion in the middle. And here is the axial velocity, high magnitude, and high magnitude of velocity here as well. So if we take a look at the pressure as well, you can see that the static pressure is quite high in this region because of this stagnation area. The flow is coming toward this wall and is being stagnated here, so the pressure is quite high in this region with a very low pressure area in this region. And so this is also the contour plot of the pressure. So if you take a look at some XY plot, let's create a surface face. I would like to make an isosurface of a line. I would like to make a line at y something around 37 here. So I'll go to surface, isosurface, the surface of constant mesh, and then I pick the y coordinate. So I click calculate. So you see that the y coordinate is changing from 0 to 44.3. So I would put the ISO values of, let's say, 38, and I call it Y38, and I just create a new surface. So this surface is now created. So if I go to XY plot and make a new one, then I would like to plot the velocity on the X direction, but on the Y38 surface. So save display. So you see that at Y38 actually the velocity close to the wall is pretty high, and is going to the lower value when it comes to the middle. So if I click on the edit again and click on axis, I don't need 3 precision for both, so 1 is enough. Then I choose this to general and this one to general as well, and if I click apply, plot again, here is the data. You see that the flow in the middle is actually the velocity is much lower when it comes toward the side walls. So if I plot the same thing for Y37, the same behavior, higher velocity toward the walls, lower velocity toward the middle. So what else we can plot? Maybe we can plot the Y plus to see if using this enhanced wall treatment was a good option, because the Y plus should be around 1, so that you can use this enhanced wall treatment. So I click on XY plot, I make a new one, but this time I have to plot the turbulence, and then this Y plus, and the Y plus direction is actually toward the Y plus direction is toward Y, and then I would like to plot the Y plus on wall 6. So, but I need to make some changes here. Precision 2 would be enough. Precision 2 would be enough, and then for Y I would like to make some changes here. 43. Then if I click on axis again, make it to 42, and general for both, I think 2 would be enough. Axis again for X, I guess, yeah. For Y I should keep it to auto range, but for X I would change the maximum to 43. Yeah. For the axis X I should use auto range. I'm making a mistake repeatedly. For X, which is the position, I don't like to use the auto range. I would like to use the range between 0 and 43, but for the Y, this should be auto range, because the Y is actually the Y plus. So I click on apply. I make sure that I don't make this mistake again this time. It seems like it's not updating, so let me see what's the problem. For the Y I'm using the auto range with the precision float, but for X I am not using auto range. I'm not sure why it doesn't apply. For X I would like to use from 0 to 43. Here it is. So here is the Y plus on wall 6, number 6, the side walls, and you see that the value of Y plus for both, actually one of them is for the right side and the other one is for the left side, and you can see that the Y plus is much lower than 1, and this tells us that the use of enhanced wall treatment was a good option, and is actually covering both or resolving through the viscous sublayer and the buffer zones. So this was a tutorial that I would like to show you today. I hope you have enjoyed it. So what we have done today was actually we set up a simulation, a 2D axis symmetry co-rotating disk. We actually set up a 2D model with a swirl using a rotational frame of reference, and then we use this RNG K epsilon model, and we calculate the solution based on the pressure-based solver, and finally we showed vector plots, contours, XY, plots of radial velocity and Y plus. I hope you have enjoyed this video. Until next time and more complicated tutorials, have a good day. Bye bye.